Today we learn about a growth model that is neither linear, nor exponential, nor logistic. So remember, a sequence of numbers is just an ordered list of numbers. Here's a new sequence of numbers. It's called the Fibonacci sequence. It goes 1, 1, 2, 3, 5, 8, 13, blah, 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 etc. So we use shorthand to be able to talk about any number in the list. We denote this sequence as f sub n, and n represents the address of the number in the list. What number in the list is it? So the first number, f sub 1, represents the first number in the list, which is 1. F sub 2 represents the second number in the list, which is 1. F sub 3 represents the third number in the list, which is 2, etc., etc. So you should note that each number in the list is the sum of the two numbers before it. So the next number in this list should be 8 plus 13, which is 21. Okay. So that would be F8, 21. And F9 should be 13 plus 21, which is 34. And F10 should be 21 plus 34, which is 55. So we can build the whole list if we just know the first two numbers, 1 and 1, 1 and 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 and 21 is 34, etc. So if I want to write a recursive formula for the Fibonacci numbers, I would say, okay, well, f sub n, the nth number in the list, is the number right before it, f sub n minus 1. We've used that notation a lot. The number right before the nth is the n minus 1, plus the number 2 before it. So the number before the nth is the n minus 1. The number 2 before the nth is the n minus 2. So my recursive formula is f sub n equals f sub n minus 1 plus f sub n minus 2. The two starting numbers, f1 and f2, they're both 1 for the Fibonacci numbers. They're called the seeds. There's also an explicit formula for the Fibonacci numbers. It's called Benet's formula, but it's pretty unwieldy, and we're not going to get into it. Your homework in my math lab might suggest that you use Benet's formula to find a Fibonacci number. Just ignore that advice and find it another way. So if you know F39 and F40, you can just add them together to get F41. So I'm just going to add those two numbers, grab my calculator. I have 63245,986 plus 102,334, 155. So that comes out to 165580141. And F42 is F41 plus F40, the two numbers right before it. So I'll take this number that I just wrote down and I'm going to add F40 to it. So plus 102,334, 155. And I get 267914296. So who is Fibonacci? Well, his real name was Leonardo of Pisa. Fibonacci means son of Bonacci. His father was nicknamed Bonacci, meaning good-natured. His father directed a trading post in Africa, in Algeria more specifically, and Leonardo traveled there, learned about Arabic numerals, and did a lot to introduce them to Europe. Trying to do even simple arithmetic using Roman numerals is pretty awful, and that's what Europe was using at the time. So Roman numerals versus Arabic numerals, yay for Fibonacci. So, but the work that he's most known for is a book called the Liber Abaci, written in 1202. It introduced the Fibonacci sequence in terms of a rabbit population. A certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from a pair from that pair in a year if it is supposed that every month each pair begets a new pair, which from the second month on becomes productive. So we may or may not, we're probably not going to watch this video right now, but just know that this problem leads to the Fibonacci sequence 1, 1, 2, 3, 5. And the Fibonacci numbers show up pretty frequently in nature too, aside from the rabbit problem. The number of petals on flowers and the number of spirals in pine cones or in sunflowers tend to be Fibonacci numbers. All right, let's move to a seemingly completely unrelated topic. The question is, what's the prettiest way to divide a line segment into two pieces? So here I've got a line segment. Let's call the small part below 1 inch, and the rest of the segment we'll call x inches. So someone, somewhere in ancient Greece, decided that the most aesthetically pleasing way to divide the line is to cut it in such a way that this proportion holds, where the short piece to the medium piece is proportionate to, is equal to the medium piece to the whole piece. So this translates to what in terms of x? So the short piece has a length of 1, the medium piece has a length of x, equals the medium piece x to the whole line, which is x plus 1. So solving that equation for x, it's not the focus of this course, but you basically cross multiply and it becomes a quadratic equation. You may or may not have seen them before. But when you solve for x, you get 1 plus the square root of 5 over 2. So we're going to type this into our calculator and to get a decimal approximation. So let's see, the square root of 5 plus 1 divided by 2. So I get approximately 1.618. So this number, 1 plus the square root of 5 over 2, it's called the golden ratio, the golden mean, the golden section, the divine proportion, and about 1 billion other names. It's been studied since Pythagoras. And this number pops up often enough that we gave it a special name. It's called the Greek letter phi. Represents 1.618. Because the golden ratio is considered an aesthetically pleasing ratio, it often pops up in art and architecture and design, particularly with the use of golden rectangles. Golden rectangles are just rectangles whose longer side divided by its shorter side is the golden ratio. So here are just a few random examples of the golden ratio in art, architecture, and design. Typical credit cards, if you do the length divided by the width, you get something close to the golden ratio. Same thing with your Apple computer laptop. The Space Needle, think of that as a line divided in the most aesthetically pleasing way, right? So the short piece to the medium piece is the same proportion as the medium piece to the whole needle. We find the golden ratio in the ancient pyramids and in the Parthenon and in a lot of Leonardo da Vinci's work. So that's it for the lecture portion of this class. You can now start your activities and let me know if you have any questions. Your activities for this class are going to take you through the relationship between the Fibonacci numbers and the golden ratio, which we have not yet talked about. So make sure you work through these activities completely and let me know if you have questions.